Material Science for Civil Engineers, Lecture 3, Metals. Today we'll be looking at the crystal structures within a metal and the defects which, as we shall see, affects the mechanical behaviour. The different types of crystal structures, we have three possible ones: body-centered cubic, face-centered cubic, and hexagonal close-packed. Now these are the different crystal structures. BCC and FCC are very similar, but HCP is slightly different, shaped more like a hexagonal. Now this is the table for the different structures, crystal structures for metals. Usually most metals have one, but as we can see with iron and titanium, they can have more than one depending upon its chemistry and temperature. Now let's look a little bit on defects of metals. Now in reality, no metal is perfect. It contains different types of defects. One we'll be looking at is dislocations, which is very important with regards to mechanical properties. First of all, let's look at some imperfections. What do we mean? This is how a perfect atomic structure should be: perfectly aligned and symmetrical, and times by million for a metal. Now with regards to imperfections, usually, well, in all cases, this is what happens. We either have vacancies, a misalignment, or different types of substitutional atoms. So a perfect cubic crystal lattice should look like this: totally symmetrical, horizontally and vertically. But in reality, it is a bit misaligned, as the illustration shows. Now there are different types of dislocations. First of all, let's look at an edge dislocation. In an edge dislocation, it is where there appears an extra half plane of atoms, as denoted there. As a result, the bottom half of the diagram is slightly aligned, and this is the symbol for an edge dislocation, and that is the extra half plane of atoms. Now what is a screw dislocation? This is caused by a shear force or shear stress. So as we can see, the atoms are kind of misaligned to the right or to the left, and this is a screw dislocation, and it has this symbol. Now in reality, all metals have a mixture of both edge and screw. Now in the elastic state, dislocations don't move. They only start moving on the onset of plastic deformations. Now the easier it moves, the weaker the material. The more difficult it is, or more slowly they move, the stronger the material. So if we can make it as difficult as possible, it makes the metal far stronger. Now, this is how the dislocations move. But just imagine there are tunnels within the metal, just like an underground system. That is how the dislocations move. One thing to bear in mind is that in brittle materials or brittle fracture, the dislocations do not move. They only move when the yield point is reached, but brittle materials fail at the yield point. Now, what are the different strengthening mechanisms? Well, there are different types. We'll look at 4: reducing the grain size, solid solution strengthening, precipitation strengthening, and strain hardening. Let's look at grain size. Every metal has a grain or grains inside it. Now, the grain boundaries are like walls. So the more walls there are, the more difficult it is for the dislocation to move, as can be seen in the following example. The dislocation hits a hurdle, it has to kind of jump over it, and as a result, it has to change its direction of movement. It's something that it doesn't want to do. But the more grain boundaries there are, the more difficult it is for the dislocations to move, hence the stronger the material. This is just to show how grain size affects the yield strength. The smaller the grain size, the larger the yield strength. Another mechanism of strengthening is solid solution strengthening or alloying, especially when it comes to carbon addition to steel. Now what happens is, as illustrated here, the dislocation attaches itself to this foreign atom or carbon in steel, and it requires extra energy to move clear or to tear itself from it. So as a result, more energy is required. Hence, this is why the strength of steels increase as more and more carbon is added. Here are other examples in other different materials. Another mechanism to increase the strength is cold work or strain hardening. So the dislocations entangle with one another and dislocation becomes more and more difficult to move. Now, how do dislocations kind of behave during deformation? This is a graph from the previous lecture when I talked about material properties. So we have the yield strength, the UTS, the linear and non-linear part. So this is the same graph, but as we can see here, as pointed out in yellow, at the yield point, this is where the dislocations start to move. So they're static in the elastic part and they start to move in the plastic region. And after the UTS, this is where necking starts. And this is an illustration of what happens during necking. It happens between the UTS and the fracture in this region, and this is what happens to the material. Likewise, here in the next graph, we can see what happens when a crack develops and what happens as it gets larger and larger. It really expands in this region as illustrated on the diagram. Another thing that you need to be able to do is the yield stress or proof stress. This is where the yield point is not apparent, or the linear part is not fully apparent. So I'll explain this in more detail during the lecture. Further details can be found on page 18 of the handout. So this is summary of the lecture. Dislocation motion correlates to plastic deformation, and the strength is increased by making dislocation motion difficult, and there are different ways of achieving this. And then finally, this is the lab report where I show a breakdown of the different sections and how much weighting is carried with each different particular section. I'll elaborate on this in more detail during the lecture. Thank you for listening.